All right, we have an enormous amount of stuff, of course, to get through today, so go ahead and get started on the warm-up. It is another hashing problem. So take this set of 8 entries and insert it into this hash table where the hash code is just the length of the string. That's your key. But you must also keep in mind that this hash table will resize before lambda officially hits 1. So go ahead, take a few minutes, draw what the final hash table will look like. Hint, it will be in a differently sized array by the end. Go ahead, take a few minutes. All right, let's start to talk about it. So let's just go entry by entry. So our first entry has a key of A. Does anyone want to raise their hand and tell me where that initially lands in this hash table that I have drawn out here? Yeah. At index what? Sorry? Index 1, yes, absolutely, because it's a string of just A, which is of length 1. And 1 mod 5 is 1, so it pops into index 1. Okay, we've got this string AB. Who wants to tell me where that one ends up? Which index? Yeah. 2, I agree. 2 mod 5 is 2. Okay, then we have 5 C's in a string. Where does that one end up? Anyone? Let's see. Here, in front. 1, let's see. I think did you mean 1 as in 0? Because 5 mod 5 is 0. The remainder of 5 divided by 5, which is 1. which is good. Yes, I understand. Okay, so we've got 3 entries. What's our lambda right now? Does anyone remember the formula for lambda? Yeah, over here. 3/5, because it's however many things are in your hash table over the capacity of your hash table. We have 3 things in the hash table. The capacity is 5. The current lambda is 3/5. Yeah, in the back. So the C's, there are 5 C's in this string, which gives them a length of 5. We take 5 mod the capacity of the array, which is 5. 5 divided by 5 is 1. And leaves no remainders, so 5 mod 5 is 0. Thank you for the clarification. Yeah, question? So we're modding things by 5 because right now the internal capacity of the array is 5. And after we get the hash code, we always mod by table size to make sure it fits into somewhere in our table. In fact, I think the next one is a good illustration as to why we need to do that. So ABC, ABC. Does anyone want to tell us which index that lands at? Anyone new? Yeah, let's see here. Yeah, you, right there, sorry. 1. Yes, I agree. And it's because ABC has a length of 6. So our hash code function will return 6, but that's not a valid index. So we mod it by 5, and that gives us 1. Right there. Questions? Okay. All right. Then we are now at 4/5 capacity. What about A, B, C, D? Does anyone want to tell us what happens when we try to insert A, B, C, D into this hash table? Yeah, over here. We have to resize. We have now officially hit a lambda of 5/5 or 1. So we're going to resize before we put this thing in. The convention is to duplicate, make a new array, make it twice the length of the old one. But whenever we resize, we also have to do something else. Does anyone remember what we have to do in order to make sure it's in the right state? Yeah, please. Rehash what's already in there. Absolutely. So now I'm going to go back through all of my things, and I'm going to say, hey, that has a length of 1. It goes at 1. Oh, great. Thanks, Pass Casey. So you can see that a lot of them ended up in the same general location if they were less than 5. But now we can stretch out and eliminate this collision at index 1 because now there is an index 6. So on and so forth. And then also the C's ended up in 5 because now, instead of modding by 5, we're modding by 10, the new internal capacity. So now I've rehashed everything into their new locations. It's time to actually add in A, B, C, D, and that ends up going into index 4. Any questions on the resize moment there? Yes? Yeah, in this moment, it was like when the dot put got called and we realized the addition of this 5th element would trigger us, we went and resized and rehashed everything. And then we were like, okay, now that it's all ready for us, we'll add this final one back in. So it was sort of like at the initiation of the 5th element, we resized it. And then once it was on a good state, then we finally added that 5th item in there. Could you have maybe added the 5th element and then resized? Yeah, but then you would have had to rehash something for no particular reason. So I'm just doing it kind of within the 5th addition, but after, like right before, so I don't have to like put something and then immediately rehash it. Yeah? So the remainder, you're right, I didn't put the code up here. This is just how hashes work. We always are going to have a function that takes our key and turns it into some int value. But then we know in order to make it work on our hash table, we always take whatever the result of hash code is and mod it by the current table size, which might be different at different moments in time, like we've seen here. So the mod comes from our internal understanding of how hash tables go from whatever the result from hash code function is to an actual index in the hash table. Good clarifying question. Any other questions about that? These are good. Cool. Okay, and then I'm not going to even try to say that next one out loud, but it ends up in 8 because there's 8 letters there. And then finally, I think this was the question in the poll everywhere. The word 5, which I thought was so cute and tricky, is actually 4 letters in length. So it ends up at 4. And then hello world, I think ends up at 1 because I think that's technically 11 letters if you count the space, which you do. Any questions on the finality of this? Yes? If we resize before that equals like where it is after that happens, will we end up with the same thing, so just like connected column? Yes, technically you could have resized this at any point, and all of these items would have ended up in this final location, because where they ended up was based on the fact that you were then going through everything and modding by 10. So the location of where something is in the hash table is always going to be deterministic based on the result of the hash code function and then the current internal capacity. Yeah, question in the back. Do we even use linear probing? Yeah, linear probing exists in places, and frankly, if you went out into the world and you were like, I took Casey Champion's data structures and algorithms, then somebody would be like, cool, you definitely know about all the hashing collisions, and if you didn't know about linear probing, somebody would send me an angry email. I don't know why, I just want to make sure that you have everything that people expect you to have. But linear probing tends to only come up when you are trying to do like large data sets where you don't have to worry so much about the internal capacity of the array, where you have machines that can extra optimize for memory across large swaths. That's when it's generally popular. You might find a little more research. In industry, we tend to use the separate chaining a little more regularly. Yeah, follow up. In the what, sorry? Oh, sorry. That was probably just a typo then. That was me fast trying to move over from last year. Yeah, this is a separate chaining one. My bad. It does say the correct answer is 4, though, right? Okay. Then I don't know. I brain farted. Sorry about that. Any other questions? Thank you for the clarifications. Okay. Then, some quick announcements. Project 2, still out. My TAs tell me office hours, still quiet. Yeah, they're all nodding right now. So if you want a bunch of helpful TAs that are bored and would love nothing more to do than to possibly mob program help you, this is the week to go to office hours. Next week will be crazy. Whatever. I can only tell you this so many times. Exercise 3 was released yesterday. It's all about trees. Guess what today's lecture is about? And then, of course, reminder, our midterm is next Friday. If for some reason you cannot physically be in this room on 2/2, please communicate with me, preferably via email, as soon as possible. It's a very different conversation before the midterm than it is after. Great. Any administrative questions at this moment? Cool. Okay. Okay, so I am going to talk about a bunch of different types of trees for the next few days. But the intro series, my understanding is they now added the topic of binary search trees. And I say that as if I don't know, as if I'm not a 123 instructor, but I added binary search trees to 123. So I kind of expect you to know about them. But if you didn't take 123 and you took 143 or any other intro class, I am going to introduce you to BSTs really quickly. And I'm sorry for that misalignment. It's almost as if standardized education, one size fits all, doesn't work perfectly. Okay. Oh, and an aside, I'm almost exclusively going to be talking about ordering keys in a map when I'm talking about what's in the trees, but I hate having to add the little value block. It's just a waste of slide space. So you're only going to see me put numbers into the trees from here on out. They're representing keys in a dictionary type of situation. Okay. Hopefully, you are all familiar with the binary tree. Remember, a binary tree is a collection of node objects where each node has a binary or two possible children, one to the left and one to the right. We think of it as an inherently recursive structure because each of these nodes kind of recursively maintains the property of having at least 0 children and at most 2. And also, boy, do they work well with recursive code. Here's some words, hopefully you remember them. Binary search trees are a binary tree where we have added what we are going to call an invariant. An invariant is a rule that we program into our code so that others, when they use it, will know that our data structure is going to maintain this rule. To make something that was maybe just a binary tree, now the slightly more specialized binary search tree, it must always uphold the invariant for every node with key k. Everything in the left subtree is smaller than k, and everything in the right subtree is greater than k. So if we look at this example, here's 10. 8 is less than 10, so it's to the left. 32 is greater than 10, so it's to the right. 11 is less than 32, so it's to the left of 32, but because it's greater than 10, it's ultimately in this right subtree. So everything in this right subtree is greater than 10. Everything in this subtree is between 10 and 32. Everything in this right subtree is greater than 32. And so that binary search invariant applies recursively. Left is less than, right is greater than. Questions at this point? So yes, it applies recursively. There you go. Thanks, animations. Okay, so why do we care about this? Because I like to think of the binary search invariant as it's almost like adding road signs to an otherwise unmarked path. If I was to ask you to search for a specific value in just a binary tree, well, a binary tree is unordered. It's kind of like an array. It's just whatever's in there. So in order to find something, I would have to search every single node to find something in a binary tree. If you remember from intro, you did those like traversals. Maybe you drew the sailboat method, if that's kind of dusting off some cobwebs. So finding a specific value in a binary tree, linear runtime. But a binary search tree, because I am guaranteed where items are in relation to one another, instead of having to search every node, I only search one path. And in fact, it turns out that for every unique value, there is really only one possible location in the tree for it to go in relation to where everything else is. So here's some of the code for how to contains key on those items. So here we have some of our recursion. Remember, contains key, this is just a traversal now for a binary tree. If the node is null, then I didn't find it. If I found the node, return true. Otherwise, return the logical OR of a recursion to the left and a recursion to the right. It's the same code over here in the binary search tree, but now I don't have to check both left and right. I only ever have to check one. Now, technically, we're using an OR, and just so you know, Java compiles from left to right in this situation. So if you found something in the left subtree and it returned true, you wouldn't even bother to make the other recursive call. But we're pessimists, and we're always thinking about that worst case scenario. So we are going to evaluate this as if you have to explore every single node. Very convenient, since this one, you can at most only ever make one recursive call. So there's some conversations about the best and worst case. This is another example of best and worst case because, again, remember, best and worst case is about the structure of the data as it currently exists. So the best case could be like, the thing I'm looking for is at the very top of the tree in the binary tree situation, whatever random overall root happens to be. In the binary search tree, the overall root will hopefully be the middle value. Not guaranteed though, foreshadowing. So we could write some recurrences that look like this, where we can see we've reduced the number of recursive calls. But I put these question marks here because I'm curious what you think. How do we think we are reducing the possible numbers of n from each recursive call down? Remember when we were doing Fibonacci, we had like n minus 1 or n minus 2, or when we were doing binary search, we had n over 2. How do we think each recursive call is limiting the number of possible nodes I have to look at? Ooh, yeah, you're in the back. So absolutely, that seems in the binary search case, right? Like if we have a big bushy tree and I go to the left and I leave this huge full branch to the right unexplored, that's like cutting half of the possibilities in half. It's almost as if the binary search tree was named after that convenient binary search algorithm. And that has a logarithmic runtime, right? Versus in the binary tree situation, since we have to explore everything, it's like, well, we actually kind of only reduce n by 1 every time, meaning the node I'm currently at, because I have to go on and do 2. But how do we know that's the situation? So maybe that's sort of like our instinct a little bit, but I told you the binary search tree has one invariant, and that invariant is that everything to the left is smaller and everything to the right is greater. So if I happened to add items in a very specific order, like this situation here, what would have had to have happened is I would have had to add the value 8 first, and then the value 4, and maybe then the value 12. And so they would get placed in the order in which they were added in relation to the things that have already been placed. So if I added them in this sort of like start with the middle value and grow slightly from there, I could get this nice full bushy tree. But what if I added every value in descending order or ascending order? There we have again our slightly judgmental terminology. We get what we would call a degenerate tree. If we add anything into a binary search property in ascending order, let's say I started with the smallest value first 1, and then I added the value 2, I'd be like, well, 2 is greater than 1, put it to the right. And then I added the value 3, and it's like, well, 3 is greater than 1 and greater than 2, so put it to the right. And if it just continued in that pattern, you get literally just a lopsided tree or a linked list. Feels like we're really coming for the linked list because the degenerate state always seems to dissolve into that. But the reason that this ends up being important is because if I had a degenerate tree and I was looking for something, am I going to eliminate half of the possibilities whenever I go to the right? No. So a worst case scenario for my binary search tree is the degenerate tree, because to determine that something's not in the tree, I still have to look at every GD node along the way. A best case scenario is if it's this nice, bushy, full, balanced tree where at every level there's 2 or 0 children. So every time I turn left or right at a signpost, I'm reducing my possibilities in half. If you go in and you do the recurrences, that's how you get the logarithmic runtime to find something in a binary search tree versus the linear runtime to find something in the degenerate tree. Questions about this idea of structure influencing runtime? Yes? Ooh, thank you for noticing. Let's walk through it. So 18, correct to the right of 8, correct to the right of 10, but is it appropriately correct to the right of 12? No. Thank you, my friend. I agree. This breaks the invariant property. My guess is that once upon a time was, I don't even know what it was supposed to be, but the 18 was probably supposed to be over here, so on and so forth. So ignore that 18. It breaks it. Does everything else pass it, though? Cool. Any other questions about the structure? Okay, great. So we will find, as we dig into trees today and Friday, that the height of the tree ends up being one of the main influencers over the runtime. Because if you think about how the recursion works, recursion always passes along to your children, which in our tree diagram is like the next level of the tree. And often the way that we reduce runtime is to reduce the number of recursive calls we have to make. It's sort of like if we wanted to have a faster loop, we need fewer iterations. If we want to have a faster recursion, we need fewer recursive calls. And to make fewer recursive calls in a tree, that means we want short trees, short, thick, bushy trees. We are going to measure that with something called height. The way that we calculate height is specifically for some math stuff, and it's a little annoyingly unintuitive. The way we count height is by the number of edges in the longest path from the root to some leaf node. So what that means is, in this type of tree here, I start at overall root, and then I find the longest path, which is this 1 to 7, and there's 1, 2 edges between overall root and 7, so we say that height is 2. If there was another node hanging off the 7, that would be a height of 3. Yes? Are edges referring to the arrows in between the nodes? Thank you for the clarification. The edges are the arrows in between the nodes, the connections between the parent and the child. It's graph terminology, and I guess that's just living in my brain. Okay, so then we've got these other kind of weird situations. So if I just have just the root, we say that has a height of 0. I like to think of it as like a bulb, just kind of stuck in the ground or something. So no branches, so it has no height. And so technically, if something is null, then it even has -1 height. You're like, Casey, why do we care? I promise, I'm getting there. So the BST was kind of an improvement upon the binary tree if we're trying to make it easier to find things quickly. But we realize that we still have this possibility of the degenerate tree. Can we improve upon that? Can we do something to add an extra invariant, essentially guaranteeing us the best case structure of a binary search tree, which means best case keeping it like full and bushy and thus by extension short? Meet the AVL tree. So AVL stands for Andelson, Velsky, and Landis, 3 individuals who came up with this, and I don't think they actually won the Turing Award for it, but now they get their name on my slide forever in perpetuity. And they invented this type of invariant that turns out to be simpler than the other options to implement and will guarantee us the best case structure of a tree. And it says such that for every node, the height of its left and right subtrees may only differ by at most 1. You might be like, I just wanted to say like that it was equal on either side or that it's like full or something like that. But we can't say full because we need to be able to place things according to the binary search invariant. So we can't just plug every single possible hole. And it's actually really hard to be like equal perfectly, because what if, you're building it over time and there's an odd number of items, so on and so forth. And also we need it to apply recursively, right? Trees have to have that. And so what we end up with this is let's always compare the height of the children of each individual node, and then it sort of rolls up so that you're balanced at the overall root as well. This will help us maintain a guaranteed log n runtime for locating any specific node, whether you're locating where to put that node or locating where a node exists. Now log n is the runtime from the overall root to the bottom of the tree, and by extension that means it's guaranteeing a height of log n. We're going to talk about this in a lot more ad nauseum. I know that sounds mathy. Okay, so let's talk about measuring balance. So we've got a few trees. So we've got this 8 that has 7 to the left and 9 to the right. Is there a height difference at 8 between its left and right subtrees? No. So, okay, great. It is what we would call balanced. Now, if we have this one over here, where we have 7 to the left of 8 but no 9, there is a difference, but that height difference is 1. Because technically the way we calculated height is the height of this subtree 7 is 0, because 7 doesn't have any children. And the height of this right subtree is -1, because it doesn't exist. So that's why we had to do that weird height stuff a couple slides ago. So the differential in height for this is between 0 and -1. That's at most 1. It still passes the invariant. Maybe a little bit more directly applicable, we can see that a node that just has no children or a leaf node, well, both of its subtrees are a height of -1, so that's fine. But if we look over here, this 10 looks to correctly follow the BST invariant in this situation, but its right subtree has a height of 1. Because I say 15, what's the height from 15 down? There's just one edge of levels. So this has a height of 1, the 15, but this null left child has a height of -1. That's a difference of more than 1. That's a difference of 2. This is imbalanced. Questions? Yeah? So it is going to guarantee log height within a factor of like 1 node here or there. And because that 1 node here or there essentially accounts to like a negligible difference in big O, we would say it's got a height of logarithmic. And I'm going to show you how it guarantees it. But this sort of balance property will apply recursively at every level of the tree. So thus, that means from the smallest leaf node all the way up to the overall root, they are all going to be at most a differential of 1 in height across the left and right subtrees. Yes, question? On your previous slide, you said that like the height would have been 2. Are we counting from the left, like the root down? So the overall root 10 has a height of 2. And then we ask 10's subtrees, which are the one that starts at 15 and then this null one, are they a differential of more than 1? So 10 has a height of 2, 15 has a height of 1, the null has a height of -1, so that's where the differential comes in. Cool. Okay. Exercise problem. Take like a minute. Is this a valid AVL tree? Look at it. Talk to those around you. Go ahead. Okay, in the interest of time, let's talk through it. So for something to be considered a binary tree, it actually has to resolve 3 separate invariants. It has to be a binary tree, which means each node has to have between 0 and 2 children. It has to be a binary search tree, which means left is less than, right is greater. And it has to be a balanced tree, which means the subtrees of a differential of at most 1. So let's start with the first one. Is this a binary tree? I see general nodding. Yes. Is this a BST? I also see nodding. I agree with you. I don't think I broke the BST invariant in this one. Okay, the more difficult one, is this balanced? And if the answer is no, does anybody want to tell us what node they might think may be imbalanced? The hesitation after you all nodded that it was an AVL tree, you are correct. I was just trying to see if you were really sure. You're right, it is an AVL tree. I know this area over here maybe feels imbalanced, but again, we look at it recursively. So I kind of start from the bottom. I'm like, is this 13 balanced? Yes. Is this 12 balanced? Well, the 11 has a height of 0 and the 13 has a height of 1. That's okay. Then I move up to the 10. The 12 has a height of 2. That's its longest path. And the 9 has a height of 1. So that's okay. And then I move up to 7. And I see that 10 has a height of 1, 2, 3, because its longest path is there. And the 4 has a longest path of 2, either of these. So that's okay as well. Any questions about that? Let's do it again. Go ahead. Talk for a minute. Is this invalid AVL tree? Okay, let's start with the invariants that hopefully are more familiar to us. Is this a binary tree? Yeah, I agree. Is this a BST? And if the answer is no, which node violates it? Anything inappropriate BST-wise? It is a binary search tree. Is it balanced? Oh, wow, pretty universal head shaking. Okay, great. Does anybody want to tell us which node they think is imbalanced? Yes? Yes, I agree. The 8 is imbalanced because the subtree, whose overall node is 12, has a height of 2. That's this pathway here. And the 7 subtree has a height of... I'm so sorry, not the learners. That probably sounded terrible. It's as if the UW should invest in better mics, but that's fine. This is officially imbalanced. Any questions on that? Yeah?
Do all binary search trees have to meet the AVL invariants?
Do all binary search trees have to meet the AVL invariants? No. If it feels relative, you can think of a binary search tree as a rectangle and an AVL tree as a square. It's a type of rectangle, just a more specific limited subset. It's got invariants that make it more specific. So not all BSTs are AVLs, but all AVLs are BSTs. Okay. So when I was literally in 373 as an undergraduate. This was P3. It was go program an AVL tree. But somewhere about 5 years ago, even the majors only course decided that that was cruel and unusual punishment, because even though I said that this invariant was the simplest to implement, it is sort of universally known in industry as a pain in the booty to maintain AVL code, so you don't have to do it anymore. But I'm going to show you the fun animation stuff about how these are officially your hopefully first introduction to what we call self-balancing trees, so that in order to maintain the balance invariant, whenever something is added to your collection, you're going to rearrange that collection to maintain the best case scenario. These are what we call rotations. So, what happens when we do an insertion that breaks the AVL condition? And it's at that moment we are going to fix it. Because that's the thing about invariance. We can let an addition break it, but then we have to go immediately fix it. It's kind of like the warm-up, how we were like, ooh, if our invariant in that scenario was that we had to resize so that lambda never hit 1, we have to take new things in, but we had to restructure under the hood in order to keep that promise to ourselves. That's the same thing happening here. So let's say I have the tree that looks like this. It's got an overall root of 1. It's got a right subchild of 2. Is this a valid binary tree? Yeah. Is it a valid binary search tree? Yeah. Is it a valid AVL tree? Yeah. Is it still balanced? No. In fact, this is the moment that it becomes imbalanced, because 1's right subtree has a height of 1 and its left subtree has a height of -1, too much differential. So we know that we need to maintain the binary search property, so we still need to maintain this relative ordering between the 1, the 2, and the 3. So we do what we call a rotation. And you just kind of take that line and you shift it to the left so that 2 becomes the overall root, adopting a left child of 1, and 3 can remain its right child. Is this tree here now balanced? That's how the rotations work. Yay, great. Okay. So I kind of think of it as when you get, this is called the line case. When you get a line where you have a node at this moment here, a node at 1 that has a height of 2, and that is imbalanced, we are going to sort of grab in the middle, and I think of it as kind of like grabbing and pulling upward, and that sort of almost like upward motion pulls the middle value up towards the overall root of whatever that thing is, which makes sense, right? In binary search, the middle value being at the top root seems to produce more balanced trees. And by kind of pulling upward, it's kind of taking that previous root and it's sort of like falling down to become a child thanks to this theoretical gravity I'm inventing inside your computer. This is what we would call a left rotation, because the tree was like imbalanced to the right. We're going to push it back to the left. Here is some more explanations of it, because remember, it applies recursively. So I've been showing you trees where it was just 3 nodes, but you might have a situation where any of those nodes have their own subtrees. And so all this is happening here is this is the same line that we just looked at. But what if those things happen to have their own subtrees? Well, this is the final form. And on your homeworks, your exercises, you have to draw some of these rotations. So you can look at this and think, okay, look at A's original left child stays. A's right child becomes what B's left child was, which makes sense. It's the subtree between them. And that's maintaining the binary search property. So it's kind of like in that gravity shift, the thing that would have gotten squished in the middle, well, we take that from the left of B and put it to the right of A. That maintains the binary search property. And now that we've freed up the left child of B, B can then adopt A as its left subchild. Questions? Not enough rotations? Guess what? There's a right-hand version of this. Imagine you have A, B, and C going to the right. Well, then you have a right rotation. It's exactly the same idea where the middle value becomes the overall root. The thing that would have gotten squished becomes A's left child. See how this like triangle with the value 3 in it goes from being B's right child to being A's left child? That frees up B's right-hand child to now adopt what was previously its parent. Okay, questions on these rotations so far? Yeah. How do we know which rotation to do? So I'm deciding that I'm going to trigger a rotation at the moment I know something's imbalanced. And the moment I know something's imbalanced is I'm actually going to have special nodes where I maintain the height of each tree, and you sort of update that recursively. You don't have to write that code, but assume the code knows the height of each node knows its own height. At the moment you realize that things are imbalanced, that node is A. And so if you are A, then really you just need to decide, am I a left rotation or a right rotation? But no matter what, the immediate child to the imbalanced way, that's going to be your overall root. So the B, whether it was the left or right case, is always the root, the new root in this context. Yes?
So A keeps its right subtree, but inherits B's right subtree.
Yes. Absolutely. This is me strategically trying to not say the words right and left about 1 billion times because I will mess it up. Not enough rotations? Okay, what if we instead had added things 1 and 3? This looks like a valid binary tree, looks like a valid BST, looks like a valid AVL, but what if I added the 2? It looks kind of like the line case, right? Like we can tell that the subtree of 3 has a height of 1, and the subtree of null has a height of -1, so there's an imbalance. But if I did a rotation, it wouldn't solve the problem. So I have to do 2 rotations to get it back into place. So what I do in this particular scenario, so the other ones were called the line case. This is called the kink case because there's a kink in the line, okay? That is the definition of kink in this class. Thank you. In order to resolve this, we are going to do 2 rotations. We are first going to rotate one of the smaller subtrees, that 3 and 2, to get us into the line case, and then we rotate the line case. And here you can see all of those, whatever. Yes, here you go. Here's your diagrams in order to make that happen. Now, you're going to get a chance to practice these on your exercise. You're going to get a chance to practice these in section next week. I'm probably going to do a warm-up with you on rotations on Friday so we can work through this. But this is the kind of thing that, honestly, it's just not easy to lecture on. Like, you kind of got to sit down and, like, move the pointers around in your head. But I just want to take the last minute here. Oh, and look, I added more examples for you so you can follow it. Oh, yeah, past Casey thought she was so cool with all those animations. There you go. Okay. So the last thing I just want to leave you with is because we're rebalancing at every moment in time that we possibly break the invariant, we maintain the height invariant. So find key will always be log n time. But what about put? What about those rotations? Do they impact the runtime? Well, as it turns out, the rotations actually end up being a constant number of reference reassignments, even if you kind of rotate back up. And so the runtime from the rotations does not change the complexity class. So this invariant ends up guaranteeing that anytime you find key or you put key into an AVL tree, you get logarithmic time. Perfect. It's 4:20. All right. Thanks so much for being here. Come back on Friday. We have more self-balancing trees to learn.